here are the notes for 2.7. For BC Calculus, we're going to look at the area bound by a polar curve, and we're going to be looking often at situations where you might be looking at area between two curves. So you're going to see a slightly different formula. If I scroll back up a little bit to the 2.6 notes, remember we have two different formulas that we're going to be looking at. One where there's an area bound by one polar curve, which we practiced in 2.6, and then this formula where we are subtracting the square of the radii inside the integral, where the two radii are from the different shapes, is going to be what we are using today. The larger radius would come first, the smaller radius would come second. Sometimes people are a little confused about what larger and smaller radii would look like in this situation, so I'll make sure and emphasize that when we do some examples. All right, so example 1, we want to sketch and set up an integral expression to find the area inside the graph of r is equal to 3 sine theta. And we also want to be, so we want to be inside that graph, but outside the graph of r equals 2 minus sine of theta. We're not going to evaluate it. We cannot use a calculator. We are just going to set it up. We want to start with a diagram. So in this situation, we have a circle with a diameter of 3, and it's a sine circle. Therefore, it is lying along the y-axis. Sine would always be along the y-axis. You might notice my circle is not perfect. It doesn't have to be a perfect circle in order for us to get a nice idea about what's happening, and that's really what we're looking for. All right, I also have r is equal to 2 minus sine theta. Well, this is a limacon with a dimple. Okay, you could say limacon, 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 all the different ways. But I know that this says not a cardioid because of the fact that A and B are not the same. And I know this is one with a dimple, limacon with a dimple, because of the fact that A is bigger than B. Now, kind of knowing that will help me as I draw this. I'm just going to put in some values for sine. When theta is 0, or values of theta, when theta is 0, the sine will zero out and I would just get a 2. That's also going to happen when theta is pi, because sine of theta, or sine of pi is 0. When I use theta as pi over 2, I get 1. That would be 2 minus 1, which is 1. This is going to be the tip of like where the indentation is of the dimple. And then if I use 3 pi over 2, sine of 3 pi over 2 is negative 1. That'd be 2 minus negative 1, which is 3 in the direction of 3 pi over 2. So my limacon with a dimple looks something like this. Kind of like a cardioid, but a cardioid is always centered on the origin where that dip of the heart would be. Okay, so what I'm going to shade the actual region that I am wanting to find. I want to be inside the circle, but outside the cardioid. I'm looking at this region right here. This is the region I would like to find. So my formula that I'm going to use will be 1/2 of a definite integral. I'm going to need to figure out what alpha and beta are for the limits of my integral here, of the big radius squared minus the small radius squared d theta. This is what I'm looking for. Okay, so starting off with, where is it that I am wanting my integral to start and end? Well, that's going to occur at the edges of my shading, which is where these two different shapes intersect. So to find that, I'm going to set my two shapes equal to each other. I cannot use a calculator, but I'm going to solve this. I'll combine like terms on the same side. I'd have 4 sine of theta is equal to 2, and I'm looking specifically where the sine of theta is equal to 1/2, positive 1/2. So I'm looking in the first and second quadrants. Well, that's going to happen when theta is equal to pi over 6 and 5 pi over 6. Those are going to be the limits of my integration. I'm going to actually draw those angles in as dotted lines. This is pi over 6, and this would be 5 pi over 6. Now, the reason I like to draw them in as these dotted lines that go to the origin is because I want to remember what happens as I draw. Remember, you've seen me draw like the fan shape before when I'm drawing in these shapes. So imagine, I'll start with a blue marker here. If I was drawing the circle starting at pi over 6, here's what my radii would look like. And I'll stop drawing this at 5 pi over 6. Now, and again, my limits of my integral are going to be those points of intersection, pi over 6 and 5 pi over 6. And if I use those blue radii, I actually have too much area. If I then look at what's happening with my limacon, with a dimple for pi over 6, I would be using these orange radii. And what I'd like to do is take the blue radii and subtract off from them the orange radii. But again, my radii need to be squared. When we talk about the biggest radii, we mean the one that's farther from the origin, at least on that interval. The lowercase r squared will be the radii that are closer to the origin. So the radius that's farther away on this shaded region that I'm looking at would be 3 sine of theta, quantity squared. And then the radii that are closer to the origin would be 2 minus the sine of theta. And again, I need to do quantity squared d theta. And then I can stop the problem. Now, we could, because this is symmetrical on the left and the right side, we could have done maybe twice the right half or twice the left half and had different intervals. So, such as pi over 6 to pi over 2 or pi over 2 to 5 pi over 6. That's one option. But we would want to double. We would want to double the 1/2 in the front. All right. Actually, I should add in one more pair of grouping symbols. All of that is d theta. All right, example 2. I encourage you to stop and pause and look at this one. This one has some extra things about it, but why don't you at least try to graph it and then restart the video. So on this one, I want to sketch and set up an integral expression to find the area of the common interior. That's something different than the region between. So we're gonna want to think carefully about this. For r is equal to 3 cosine theta and r is equal to 1 plus cosine theta. Well, r is equal to 3 cosine theta is a circle with a diameter of 3, and this is going to be using a diameter right here along the x-axis. R is equal to 1 plus 1 cosine theta is a cardioid since A and B are equal to the same value. And so this is going to be a heart shape, and if I graph this, I'm going to actually improve my circle just a little bit to make sure I'm staying over on the first and fourth quadrants. That's better. Our 1 plus 1 cosine theta, if I put in 0, I would get 1 plus 1, which is 2. Oh, let me change colors here. If I put in pi over 2 for theta, I would get a 0 for that, plus 1. Same thing will happen at 3 pi over 2. And if I put into this equation pi, I would have 1 minus 1, which is 0. Remember, cardioids always go to the origin. That was close. Try again. Something like that. Now notice cardioids also always dip into the other side of like the y-axis here for these cosine cardioids. The common region would be the region that's inside both the circle and the cardioid. Now I'm going to start this one in a very similar fashion to what I did with the last example, where I really want to find out where do these shapes intersect. That's actually super, super important. Where do these shapes intersect? So I'm going to set these two functions equal to each other and solve. I get that the 2 times the cosine of theta is equal to 1. Cosine theta is equal to 1/2. And so theta would be equal to pi over 3 and negative pi over 3. Okay, because we're looking at the first and the fourth quadrant where x is positive. And I am going to draw in those lines at those points of intersection. It looks something like this. This is your pi over 3. And then also at negative pi over 3. Now it's important to draw those in because what's going to happen, and you guys will see this in a minute when we look at the shading more closely, is that some of our shaded region is on either side of these dividing lines, these dotted lines. And so you're going to need different strategies in place here. Now, all we're doing here is setting up the integral. We are not actually going to be calculating it. We're just going to set it up. So here's what I want you to think about. In fact, I'm even going to color these slightly differently. I've got the yellow region. I'm going to recolor. That is going to be between my points, my lines of intersection here. Okay, these dividing angle lines. It's mad at me. Here we go. I'm going to color these in as yellow. That's not the only region I want. Also, as part of the common interior, I'm going to, I'll color this pink. I want these parts. These parts right here are also inside both the circle and the cardioid, but they're on the other side of those dotted lines where my angles are at. And I'm going to need to think about them differently. Here's why. Let me draw some lines in here. I'll start with some purple lines. If I'm looking at the cardioid and I'm doing the radius of the cardioid from negative pi over 3 to 0 to pi over 3, you'll notice that the yellow shaded region is formed by the radii that come from the cardioid. However, if I want to look at the pink region, that will be formed from pi over 3 to pi over 2 by my circle. Notice it's not matching up the outline of my purple cardioid. It's matching the outline of my green circle. So we want to choose the appropriate radii. This is not a situation where we're doing area between two shapes. Instead, this is a situation where we have regions formed by different shapes. So here's kind of the plan that I'm going to use here. I want to find a way to represent the area of the yellow region plus the area of the pink region. It kind of looks green now because I've colored in the radii here. Maybe I'll just call it the green region. But those all form the common interior. Well, my yellow region could be formed by just one polar graph from negative pi over 3 to pi over 3 of, remember my yellow was formed by the cardioid. Look at where the outline goes to. That was from the cardioid, so that's the radius of the cardioid quantity squared d theta. That's the yellow. For the green, there's really two green regions, and they are not adjacent to each other. I would want to either find the area of each one and add them up, or I could do twice the area of one, which is what I'm going to do. I'll do twice the area of one of them. You can pick which one. I'll pick the top one. That top one starts at pi over 3, and it goes until we hit that 0 down here up at pi over 2. And then this would be formed by the circle. So the radius squared needs to come from the circle here. This is one of multiple ways that we could have written this. I could have, and then I could just write that as a 1. I could have chosen, if I wanted to, here with the yellow, to do this differently. I could have done twice the top half and just gone from 0 to pi over 3 if I wanted. I could have also done twice the bottom half.